All right. Hello, everyone, and welcome to Calculus. Today, we're going to be talking about the introduction to limits, and I will be your teacher for the day, Dr. Moore here. So, motivation. So, limits are basically a lot of what's going to underlie all of calculus. So, it's really important that we understand them so that we can use them in more interesting contexts. And so today, what we're going to be doing is really going through a more graphical intuition about limits. And then the next day's videos are going to go into a more careful mathematical definition. And basically, sort of the summary of limits is they're talking about like what's happening near a point in a function, but not what's happening necessarily at that point in the function. And that's going to be a very, very important difference. Okay, so calculus is going to study how variables are changing over time. And what we're doing today is we're going to see how the values of the function changes as the independent variable changes. So as x is changing, what is y doing? And so intuitively, we've got, a bunch of examples that we may care about between independent and dependent variables that we may have seen in other classes. So time versus water depth, air temperature versus volume, cost of advertising versus profit, time versus velocity. All of these sorts of things are things where we may care about the limit of the value of our function. Okay, so formally, what the heck is a limit? So this notation down here is how we will write it down. So this is the limit as x approaches a of f of x, and we say it equals some value c. And what this means, if we look at our definition above, it means that as the x values are getting closer and closer to a, then the y values, f of x values, are getting closer and closer to c. That's what we care about. So as x gets closer to a, y gets closer to c. Okay. Again, this is for x values close to a, not x equal to a. And what that means is we only care about the stuff that's happening around a, not actually at a. So the actual value of our function at a does not matter at all. We don't even need it to be defined there. And that's going to be the big difference between how we normally think about functions versus thinking about them through limits. Okay, so for a very basic example, this is going to be a place where what's happening around a matches what's happening at a. Right, so if we think about our x values, getting closer and closer to 3. Right, so maybe I take my x values starting here. Ooh. And getting closer and closer and closer to 3. So I'm thinking about sort of a sequence of x values. So then if I look at the respective y values, I'm over time, what my y values are doing. So that's again the height of these points that I'm seeing. The y values seem to be getting closer and closer to 2. So I start with x values. I look at the points on the graph and look at what the pattern the y values are doing. So as my x values get closer to 3, my y values are getting closer to 2. And that's actually also true. It's important to check this kind of from both sides. So this is an example of checking from the rightmost side. We're going down to 3, and our y values are getting close to 2. It's also important to check from the other side. So if my y values are going up to 3, if my x values are going up to 3, what are my y values doing? Well, let's look at my points. These are sort of the corresponding points. And so the y values, they seem to be going down to 2 as well. So it doesn't matter which side I come from, my y values are getting close to 2. And so because of that, we get to say that the limit as x approaches 3 of f of x is 2. In other words, as our x values approach 3, our y values are approaching 2. Now, okay, this seems pretty intuitive because like our function, our y value at 3 is 2. So that feels very reasonable thing to say. And so here's an example, just slightly altered, where it's still true. So in particular, our function is now not defined at x equals 3, but the limit as x approaches 3 is still going to be 2. Because if we do that same thing as before, where we take x values and we approach 3, and we look at the corresponding points, and then the corresponding y values, our y values are still approaching 2, even though our function is not defined exactly at x equals 3, we still have the pattern that the y values are getting closer and closer to 2. And so this is how it's slightly different than saying that f of 3 equals 2. It's saying near 3, f is getting close to 2. And then here is one more example, again, slightly altered. And we can still see that in this problem, no matter which direction you come from, as x gets close to 3, our function is getting close to 2. So if we come from, say, the right-hand side, and we let our x values get closer and closer to 3, and we look at the corresponding points, and then the corresponding y values, we see that the y values are getting closer and closer to 2. Or, again, if we look from the left side and let our x values get closer and closer to 3, look at the corresponding points, and then the corresponding y values, the y values are getting closer and closer to 2. So from either side, no matter how you approach 3, your y values are getting closer and closer to 2. And so we get to say that the limit as x approaches 3 of f of x is 2. Okay. Now I've been kind of making it sound like limits always exist. That's not necessarily true, right? We could have a pretty complicated function where things are a bit messier. And so how could that happen? There are a few different ways. So one, like I said, it's really important that the function approaches the same place. If we look at x going towards our a value from the left versus from the right. So if we kind of had different things going on as we approached from the right of the function versus from the left, then the limit would not exist. We can also have the function basically being too busy or oscillating too much. So that way it's not really approaching any one value. It's just way too messy. There's not a nice little pattern that's happening. And then the other thing that we can have is we can have our function approaching infinity from one or both of the directions. So here's an example of approaching different values from the left versus the right. So if I want to think about approaching x equals 2, right? So if I approach from the right, and I look at the corresponding points on my function, and then the corresponding y values, my y values seem to be getting closer and closer to y equals 3. So approaching from the right, I'm getting close to y equals 3. But if I change that up and I approach from the left, and I look at the corresponding points on my graph, and then the corresponding y values, the y values seem to be getting closer and closer to 2. So on the right, we're getting close to 3, and on the left, we're getting close to 2. Since those don't match, we say that the limit does not exist, because it's not any way that I approach 2, my function gives a particular number. We can also, as I said, have a function that oscillates too much or is too busy. So basically, if you try to do what I've been doing of taking x values that are getting closer and closer to 0, your corresponding points, I don't even know where to draw this, are they're going to be jumping around too much. So if we then look at the y values, this is my first point, second y value, see, third y value, fourth y value, fifth y value. Like if you look at all of those y values, they're jumping way too much There's not a pattern. They're not clearly getting closer and closer to a particular number. They're jumping around. And so because of that, if you look from the right or from the left in this one, you're going to see that you just don't have a nice pattern to the y values, and so the function's limit will not exist at x equals 0. All right. And so the last case that we can have limits not exist is when we're talking about approaching infinity, so we need to be careful here. So let's look at these sort of 3 examples of ways that limits could or could not exist involving infinity. So in this first picture, if we approach x equals 2 from the right, then we see our y values are going off to positive infinity. On the other hand, if we come from the left, our y values seem to be going to negative infinity. And so because of that, our left and our right-hand sides don't match. So this is going to be a does not exist situation. Similarly, in this problem, if I approach x equals 2 from the right, then my y values are going off to positive infinity. But if I approach x equals 2 from the left, my y values are all 3. Those don't match, so limit does not exist. In this function, though, as I approach x equals 2 from the left, or from the right, my y values go off to positive infinity. And as I approach from the left, my y values go off to positive infinity. So in the first two, my limits are not going to exist as x goes to 2. But in this one, we do get to say that the limit, so in this last function, the limit as x goes to 2 of f of x is indeed infinity because it matches on both sides. So be careful when you've got some infinities and make sure you're still checking for the matching on both sides. Okay, so now is your chance to go ahead and try it yourself. So I've got a graph here, and I would like you to pause the video here and go ahead and try to find each of these limits. And I will show you the answers in just a second to be able to double check yourself. But yes, pause here. Okay, I'm assuming you are back from having paused. So these are the limits that you should have gotten. As x approaches minus pi over 2, f of x should be approaching minus 1. As x approaches 0, f of x should also be approaching 0. As x approaches pi over 2, f of x, its limit should not exist. And then lastly, the limit as x approaches 3 pi over 2 of f of x is minus infinity. And then just one more thing for you to think about. So we can also, again, put this in terms of applications. So let's say, for example, we're analyzing a growing population of dragonflies. You start out with 2 female and 2 male dragonflies, and then you kind of keep checking over time and seeing what the population ends up being. So we end up with this data set. So, for example, when you have 3 female dragonflies and 5 total dragonflies, then you'll see that you have 13 females and 18 total dragonflies and so forth. And so the question for you is, based on just this data set alone, what do you think, what percentage of dragonflies would you eventually expect to be female? And how many females do you expect to see for each male dragonfly? So again, pause here, think about this for a minute, come up with your answer, and then unpause and I'll let you know. Okay, so we're looking at about estimating based on sort of we think about this as percentages of the population and so forth. It looks like the percentage is bouncing around 66%. And so you would expect about 2 females per each male dragonfly. All right. Congrats, y'all. That was your first calc video.